In the annals of 19th century physics, a period of remarkable intellectual ferment, George Gabriel Stokes emerged as a preeminent figure. His 1850 paper on the theories of the internal friction of fluids in motion and of the equilibrium and motion of elastic solids represents the watershed moment, cementing Stokes' legacy and laying the groundwork for subsequent advances in fluid dynamics and continuum mechanics. The work wasn't merely a compilation of existing knowledge, it was a synthesis and extension of prior work, addressing fundamental questions concerning the behavior of matter under stress and motion. The paper's influence, though initially subtle, resonated deeply, shaping the trajectory of scientific inquiry for decades. The intellectual context in which Stokes operated was one of accelerating understanding. Previous work, particularly by Navier and Poisson, had already begun to explore the mechanical properties of fluids and solids. Their efforts, valuable as they were, suffered from certain limitations that Stokes aimed to overcome. Navier, in his 1823 memoir, had proposed equations of motion for viscous fluids, yet these equations contained a degree of ambiguity and were based on assumptions that require further clarification. Poisson, working independently, had contributed significantly to the theory of elasticity, but faced challenges concerning the nature of the stresses within solids. Stokes, inheriting this intellectual inheritance, recognized the need for a more rigorous and complete framework. He sought to refine existing models, reconcile apparent contradictions, and provide a more comprehensive understanding of how materials respond to external forces. The core of Stokes' 1850 paper involves a meticulous examination of the forces at play within both fluids and elastic solids. For fluids, Stokes started with the concept of viscosity, the internal friction that resists the flow of a fluid. He derived equations of motion that extended Navier's earlier work, notably clarifying the relationship between stress and rate of strain. These equations, subsequently known as the Navier-Stokes equations, provided a mathematical framework for describing the behavior of viscous fluids and are a cornerstone of modern fluid dynamics. The equations are complex, involving terms for pressure, shear stress, and the effects of inertia. These equations can be stated as ρ times the partial derivative of the velocity vector with respect to time, plus the dot product of the velocity vector and the del operator acting on the velocity vector equals the negative gradient of pressure plus mu times the Laplacian applied to the velocity vector plus the vector of the external forces, wherein ρ represents the fluid density, velocity vector, t is time, del is the nabla operator, pressure is pressure, mu is the dynamic viscosity, and the external forces vector. Even today, the analytical solution to the Navier-Stokes equations is limited, but the equations' profound importance endures. This is because they are critical in calculating problems in fluid dynamics, leading many practical applications such as weather forecasting, airplane wing design, and understanding blood. Stokes' analysis extended to elastic solids, addressing the challenges inherent in understanding their deformation under stress. He formulated equations that described the relationship between stress and strain within an elastic material, building on the existing work of Poisson and others. Stokes meticulously considered the forces acting within the solid, including the internal stresses and the external loads. He also made an important contribution by clarifying the concept of the bulk modulus, which quantifies how much a substance compresses under pressure. This clarified how the elastic properties of solids and fluids are described. He considered the propagation of waves in elastic solids, resulting in predictions that were subsequently confirmed experimentally. The immediate impact of Stokes' paper, while significant, was perhaps less dramatic than the eventual reach of his contributions. His contemporaries, while recognizing the paper's rigor, did not immediately grasp the full extent of its implications. The mathematical sophistication of his analysis, the novelty of his approach, and the complexity of the problems addressed all contributed to a cautious reception. The initial readership was concentrated within the scientific community, primarily among physicists and mathematicians. The equations he formulated, while elegant in their mathematical construction, were difficult to apply, restricting the immediate range of their impact. The paper, however, provided a crucial foundation for future research, offering a more complete understanding of fluid mechanics. The enduring legacy of Stokes' work is evident in the generations of scientists who followed. His equations have formed the basis of countless analyses in fluid dynamics. They are fundamental to the study of turbulence, the motion of air around aircraft, and the behavior of ocean currents. The Navier-Stokes equations, however, present challenging mathematical complexities. One of the Millennium Prize problems issued by the Clay Mathematics Institute asks for a mathematical proof of the existence or non-existence of smooth solutions to the Navier-Stokes equations. demonstrating their enduring significance and the ongoing efforts to understand them fully. The paper also influenced the development of solid mechanics. Stokes' work on elasticity set the stage for advances in areas such as structural engineering and materials science. His clarification of the bulk modulus and his analysis of wave propagation in solids were pivotal in the development of seismology. Seismologists used Stokes' work to better understand the behavior of the Earth's interior, using his theoretical work to interpret seismic data that offered crucial details about the Earth's structure and dynamics. Stokes was influenced by various thinkers whose work provided him with essential foundations. He drew on the work of Navier and Poisson. As mentioned earlier, he also deeply understood the work of Cauchy on stress and strain, recognizing the importance of their work in formulating the equations of motion. The Cambridge tradition in mathematical physics, where Stokes was steeped, was also a critical influence. His rigorous approach to mathematical analysis, his emphasis on physical intuition, and his dedication to precise formulations all reflect his training and context. These influences demonstrate a broad understanding of the existing theories and the challenges that needed to be addressed. Stokes' 1850 paper had a direct influence on many subsequent scientific developments. The Navier-Stokes equations, for example, have continued to be refined and developed by generations of scientists. Ludwig Prandtl, a German physicist, developed boundary layer theory which simplifies the equations and offered means to study the flow of fluids. G.Y. Taylor used Taylor's hypothesis to improve the mathematical modelling of turbulence. His investigation of the Rayleigh-Taylor instability led to a better understanding of chaotic systems. These advancements arose from the foundational work that Stokes had accomplished. The reception of Stokes' work has evolved over time. Initially, it was appreciated by a relatively small circle of experts. As the implications of his work became more apparent and the methods to solve them improved, his work has attained wider appreciation. It has been subjected to a diverse array of interpretations and reinterpretations. Recent scholarship has emphasized the paper's historical significance, its mathematical elegance, and its enduring relevance to contemporary scientific problems. The work has earned its place within the pantheon of fundamental scientific achievements. The equations have been modified to include compressible flow. The paper has gained renewed interest as scientists seek to better understand the nature of turbulence. In conclusion, George Gabriel Stokes' 1850 paper on fluid dynamics and the mechanics of elastic solids represents more than just a scientific treatise. It represents a paradigm shift. He refined existing models and constructed equations that laid the foundation for modern fluid dynamics and solid mechanics. The work stands as a testament to the synergy of mathematical rigor and physical intuition. Stokes, by synthesizing and extending prior knowledge, provided a framework that continues to inspire and challenge scientists. The Navier-Stokes equations remain at the heart of many scientific inquiries. His meticulous analysis of the behavior of elastic solids provided the groundwork for crucial advances in seismology and materials science. The paper's enduring influence is a profound testament to its intellectual power.